You know, at the very heart of your smartphone or that powerful AI you keep hearing about, it all comes down to one thing. A switch. A switch that is so unbelievably small you can fit billions of them on the tip of your finger. Today, we're going to crack this thing open and really understand how this microscopic marvel works and how it completely reinvented our world.
All right, so here's our game plan. We're going to follow a 5-step assembly line, if you will. First, we'll look at the raw material, silicon. Then, we'll actually build the switch itself. After that, we'll see how we've managed to shrink it down to absolutely insane sizes. Connect that to the massive computing power we have today, and then finally, we'll look at the pretty mind-bending challenges we face when we get down to the atomic scale. It sounds like something out of science fiction, doesn't it? How can you possibly take a piece of sand, the stuff you find on the beach, and turn it into the engine for a thinking machine? That's the core question we're going to answer today. And believe it or not, the whole journey from a grain of sand to superintelligence all starts with one very special secret property of its main ingredient.
Okay, so let's jump into our first section. Everything, and I mean everything that modern tech possible hinges on silicon's very particular secret power. It's an ability that, frankly, enables this entire technological revolution. And that power? It's the fact that silicon is a semiconductor. Now, the key word here is controlled. See, some materials always let electricity flow, and other materials always block it. But a semiconductor, well, you can tell it what to do. You can make it act like a conductor or an insulator, literally on command.
So think about it. If you want to build a switch, what do you need? You need something that can be both on and off. A conductor, like a copper wire, that's always on. An insulator, like rubber, that's always off. They're useless for making a switch. But a semiconductor, it's the perfect maybe. It gives us the control we need to create the ones and zeros that are the fundamental language of the digital world.
So how do we control it? We use a process called doping. The best way to think about it is like a recipe. Pure silicon is kind of neutral, a bit boring electrically. But by sprinkling in just a tiny, tiny amount of other elements, impurities, we can completely change its behavior. We can create an N-type, which has extra free-floating electrons, or we can create a P-type, which has little electron-sized gaps, or holes, for electrons to fall into. This is how we give silicon its electrical personality.
All right, let's move on to section 2. Now that we have our specially made N-type and P-type silicon, we can finally assemble the single most important component in all of modern electronics, the transistor. And specifically, we're talking about the MOSFET.
Now, a MOSFET has 4 essential parts. You've got the source, which is where the electrons come from. You've got the drain, that's where they want to go. There's the body, that's just the silicon base it's all built on. And then, most importantly, you have the gate. The gate is the control knob, it's the whole magic trick. Honestly, the best way to visualize this is as a simple water faucet. The source is the pipe bringing the water in, the drain is where the water comes out, and the gate, that's the handle you turn. When you turn that handle, you allow water, or in our case, a flood of electrons, to flow. And here's the truly brilliant part. There are no moving parts at all. When we apply a tiny positive voltage to that gate, its electric field pulls electrons up from the silicon right below it. This forms a temporary invisible bridge, a channel, connecting the source and the drain. Electrons rush across and boom, the switch is on. Remove that voltage, the channel vanishes and the switch is off. It's an elegant, silent, electrostatically controlled switch. So, we have our switch. Now what? Well, the next step in the revolution was to make it smaller, and then smaller, and then smaller again. This relentless, almost obsessive drive for miniaturization is what has defined the last 60 years of computing. In the very beginning, these transistors were basically flat, or planar, with the gate just sitting on top. But as they shrank, a big problem emerged. Electrons started to leak out when the switch was supposed to be off. So engineers had to get creative, and they had to go 3D. Around the 2010s, we got the FinFET, which stood the channel up vertically like a fin. And today we have the GAA-FET, or Gate-All-Around, which takes that 3D idea even further.
And the reason for going 3D all comes down to one word: control. The FinFET design wrapped that gate around the channel on 3 sides, which gave it a much better grip, stopping those leaks. But the GA-FET, well, that's the ultimate version. The gate completely surrounds the channel on all sides. This gives it almost perfect electrostatic control, which is what allows us to keep shrinking transistors without them failing.
Okay, this brings us to the real magic of it all, the magic of scale. A single transistor is just a simple switch. On, off. Big deal, right? But when you combine billions of them,
That's when you can create something that starts to look a whole lot like intelligence.
Think of it like a ladder of computation. You start with your basic transistor switches, and you use them to build simple logic gates, things that can make basic decisions, like and, or, and not. Then you use those logic gates to build more complex units that can do actual math. And finally, you pack millions and millions of those calculation units together to create the CPUs, GPUs, and AI accelerators that power our world.
So just how many are we talking about here? Well, a modern AI chip can have over 50 billion transistors. That is not a typo. 50 billion switches. All of them turning on and off billions of times every second. The scale is it's almost incomprehensible.
This quote really just sums it all up perfectly. The entire digital revolution, from the first calculators all the way to generative AI, has been powered by one single relentless principle: our ability to make these CMOS transistors smaller, faster, and cheaper year after year after year.
But what happens when you just can't get any smaller? In our final section, we're going to look at the bizarre new physical laws and the huge challenges that show up when your switches are only a handful of atoms wide.
You see, at this scale, the neat and tidy physics we're used to starts to break down, and the weird world of quantum mechanics takes over. We start to get all these quantum annoyances. Electrons start to tunnel through barriers they shouldn't, causing leakage. They can become too energetic and actually damage the transistor over time. The materials themselves can become unstable. Engineers today are basically fighting a war against quantum physics itself.
And a huge part of that war is all about power. There are two kinds you have to worry about. There's dynamic power, which is the energy you use when you're actually switching the transistor on and off. But then there's static power. That's the energy you waste from those pesky leakage currents when the transistor is supposed to be doing nothing. As these things shrink, this static leakage becomes a massive problem, draining your battery and generating a ton of heat.
So when you boil it all down, it comes to this. The silicon transistor, this incredible, tiny switch, has been the engine of progress for over half a century. It literally took us from sand to superintelligence. But as we start to hit the fundamental limits of atoms and energy, we're left with this enormous question. What comes next? What new materials, what new devices, what new physics is going to be needed to power the next 50 years of computation?